Let's start with today's lecture, which is related to pulse modulation technique. It covers both CLOs 1 and CLO 2, and it is 6.2 section of your textbook. The contents of this lecture are as follows. Here we will see different types of pulse modulation techniques, and then we will have a detailed discussion on pulse code modulation. So far we have studied analog modulation. In analog modulation, some parameters of the sinusoidal carrier signal are varied according to the message or modulating signal. Suppose we varied amplitude of the sinusoidal carrier, and then we varied phase and frequency of the sinusoidal carrier. So the main thing here is that carrier signal is sinusoidal in nature. But when we talk about pulse modulation, then carrier is no longer a sinusoidal signal, but it consists of pulse train. So this is basically a representation of pulse train, and it will now act as a carrier signal for pulse modulation. There are different types of pulse modulation which we will study. The first one is pulse amplitude modulation, then pulse width modulation, pulse position modulation, pulse code modulation, differential pulse code modulation, delta modulation, and adaptive delta modulation. The first type of pulse modulation is pulse amplitude modulation. In this modulation scheme, the information is embedded in the amplitude or height of the pulses. These pulses are basically our carrier signal, and we will be transferring information by changing the amplitude of these impulses. So these you can observe here that width of these pulses are same, but the only difference is in their amplitude. The second type is pulse width modulation. In this modulation scheme, the information is carried in the width or duration of the pulses. So as you can observe here, the width of all pulses is different, but the amplitude remains same. So it can be noticed that amplitude or height of the pulses is exactly the same, but the only difference is in the width. When we have highest peak of the signal or highest amplitude, then the width of the pulse is maximum, and when we are moving towards lowest peak, then the width of the pulse is getting reduced. The third type of pulse modulation is pulse position modulation. In this modulation, the information is carried in the position of the pulses. So you can observe that height and width of different pulses is exactly same. All pulses are at same height, and the width is also same. But the pulses are not centered at sampling instant. These are sampling instants. So some pulses are close to the sampling instant, whereas some pulses are far from the sampling instance. So in this way, we are basically transferring our information. This slide is summarizing the types of pulse modulation which we have studied so far. So if we assume that g of t is our signal, which is sinusoidal in nature, and these arrows are showing the sampling instants, then in case of pulse amplitude modulation, our signal will take form like this. Here all pulses have different amplitudes, but their width is same. The other type is pulse width modulation. Here all pulses have same amplitude, but their width is changing. And then we have pulse position modulation. Here the pulses width is same, their amplitude is same, but they have different locations. I mean, some pulses are close to the sampling instance and some are far from the sampling instance. So on this basis we can distinguish these different pulses. Now let's start with one of the most important type of pulse modulation, which is pulse code modulation. The basic form of digital pulse modulation is known as pulse code modulation or PCM. In PCM, what we are going to do, we have a message signal m of t, and we represent this message signal by discretizing it in both time axis and amplitude axis. So message signal is represented by a sequence of pulses which is performed by representing the signal in discrete form in both time and amplitude. So now we have discretized our signal on both time axis and amplitude axis. This form of signal representation permits the transmission of message signal as a sequence of coded binary pulses. So now we will convert these discretized signal into coded binary pulses. And what is the feature of these coded binary pulses? That these are less affected by the channel noise, and it can be regenerated at any step with the help of regenerative repeater. So different operations are performed at the transmitter side of PCM system. These operations involve sampling, quantization and encoding. We will study these operations in detail on further slides. And LPF is also used prior to sampler to prevent aliasing of message signal. We have discussed this important point in our previous lecture related to sampling theorem. And then after sampling we perform quantization and encoding, and these operations are combinedly termed as analog to digital converter. Let's have a look at basic elements of PCM, pulse code modulation. In start we have message signal, which is sinusoidal in nature. This signal is assumed to be a band unlimited signal. So first this signal will pass through low pass filter, which acts as anti-aliasing filter, and because of this filter the band unlimited signal will be converted into band limited signal. Now after this our band limited signal will pass through sampler. Sampler performs sampling and discretize the time axis of the signal. So by discretization means we are taking samples at the integer values of time axis. So here you can see that the amplitude is not discretized, only time axis is discretized. At amplitude we have values like 1.2 volt, 1.8 volt, 2.6 volt and so on. So now this sample signal will pass through quantizer. The main function of quantizer is that it converts the amplitude of this signal into discretized form, and now we have integer values at the amplitude axis. So this 1.2 volt will convert into 1 volt and 1.8 volt will convert into 2 volt. So it means we are basically introducing some error, but at the output of quantizer we will get a signal which is not only discretized on time axis, but now it is also discretized on the amplitude axis. After this quantized signal will pass through encoder. Encoder will assign different binary codes to these amplitudes, and then we will get a digital signal. Now this digital signal will pass through the channel, and due to its propagation through the channel, the shape of the signal gets affected because of different noise factors and interference factors. The purpose of regenerative repeater is to regenerate new pulses. So you can observe that it will eliminate these channel noise and we will get new pulses. Now after finishing its journey through the channel, signal receives at the receiver, and it passes through the decoder. Now decoder will convert a signal, a quantized signal which has or sample signal. So this signal will pass through low pass filter, and at the output we receive analog signal which was basically transmitted from the transmitter. These are basic elements of PCM. So the most important block here is sampler, quantizer and encoder. The first step which we are doing in PCM is sampling. In PCM, first we do sampling to convert analog signal into discrete signal. So at the start of sampler we have analog signal which is continuous on both time axis and amplitude axis. After sampling we discretized our signal on the time axis, however its amplitude remain continuous in nature. Now we perform quantization, and the main purpose of quantization is to discretize the amplitude of the samples. So in how we perform quantization is an important task. We basically divide the complete amplitude axis into different levels. These levels are known as quantization levels. Then we look at what is the amplitude of each sample. Suppose this amplitude is coming between level 2 and level 3, and this is 2.6 volt. Now we observe that either we have to round it off to level 2 or we have to round it up to level 3. So how can we decide this? This decision is based on on quantization error. So we move the level of or the amplitude of each sample in such a way that we can minimize the quantization error. 2.6 is more close to level 3 as compared to level 2, so we will round it up to level 3. In this way, although quantization error is introduced, but the amplitude of all samples is discretized. In this way we are performing quantization. After that we perform encoding. In encoder represents each of the quantization voltage by a unique binary code. Different binary codes are assigned to each quantization level, and then we assign these codes to our samples. So one important question arises here is that how many bits in one binary code are required to represent each quantization level. We will answer this question on the next slide. So the number of quantization levels and binary bits required for encoder follow the relation as L is equal to 2 raised to power n. N is showing the number of quantization levels and n is the number of bits per sample. So if we assume that we want to divide our signal into 4 quantization levels, then according to this formula 2 bits are required for encoding purpose. So 2 bits per sample are used for encoding. It means if the level is 1 and our sample is at level 1, then 0 0 will be assigned. If our sample is at level 2, 0 1 will be assigned. At 3 1 0, and at 4 fourth level 1 1 will be assigned. So this is not binary to decimal conversion, but in this way we will be assigning different binary codes to our levels. So let's start with this example. Here we have sinusoidal signal, and suppose we have performed sampling, and now we want to discretize the amplitude of this signal. So before going further, we have to decide that in how many levels we want to divide this signal. So suppose we want to divide it into 8 quantization levels, as showing from here. 0 to 7 are showing the 8 quantization level. 4 levels, 0.5, 1.5, 2.5 and 3.5. These are the quantization levels. So 4 quantization levels are at the positive side, and 4 quantization levels minus 0.5, minus 1.5, minus 2.5 and minus 3.5 are at the negative side of this at the negative side of this axis. Now if we look at this sample is this is the sample value, and it's the original sample value is minus 0.25. so this is the original sample value. Now we have to either round it off or round it up. So this sample value is basically between minus 0.5 and 0.5 quantization level. If I round it up to 0.5, then the quantization error is very high, but if I round it off to minus 0.5 level, then the quantization level is very less as compared to the other scenario. So I can write that my quantized value, that I am basically rounding this sample value to minus 0.5, and this level is 3. So binary code assigned to this is 0 1 1. Now let's talk about other sample. The actual sample value is 3.1. Okay, so this is 3.1. now this 3.1 is between 3.5 and 2.5. these are the two quantization levels. It is more close to 3.5, so quantization value 3.5 will be assigned, and then the code number is basically 7. so this is the 7th code number, and we can convert it, we can assign 111 binary code to this. So why 3 bits are assigned to each sample? Because according to the formula, L is equal to 2 raised to power n, we have L equal to 8. So when L is 8, then then the formula states that L is equal to 2 raised to power 3. So these 3 is representing the number of bits assigned to each sample. The quantization error is therefore defined as the difference between sampled output and the quantized output. So we want to reduce this quantization error while performing discretization of amplitude axis. So now the question is, how can we reduce quantization error? One person can say that if we increase the quantization levels, then the quantization error will be reduced, but this is not the ideal scenario, because there is a trade-off between quantization error and bandwidth. Because if we want to reduce quantization error, quantization levels should be increased. But what is the problem with increasing quantization error? It will increase the number of bits per sample, because when L will be increasing, then N will also be increasing. So it means more number of bits are required to represent each sample, and because of this more bandwidth is required. So it is basically a trade-off between quantization error and bandwidth. We don't want to increase the quantization error, but at the same time we also don't want to utilize more bandwidth. So if we want to calculate the bit rate of PCM, then the bit rate of PCM is calculated as RB is equal to N into Fs. Here N is the number of bits per sample and Fs is the sampling frequency. To calculate the bandwidth of PCM, it is calculated like RB over 2, and here RB is the bit rate. Advantages of PCM are that it is robust against noise and interference. Then because of this, because of the utilization of regenerative repeater, we can efficiently regenerate our pulses. When the noise is less, then overall signal to noise ratio will be improved, and then we have uniform format, and it is also providing us ease in adding and dropping, and this is also very secure. So this is all for today's lecture. Thank you.